Hi everybody, it's Dr. Chabot, and in this short video we're going to talk about the temperature dependence of resistivity. So let's remember what resistivity is. So we have this equation that delta V equals IR, and this R was a resistance that depended in part on the properties of the material. So R was equal to rho L over A, and I'll call this rho sub R, where the rho sub R is the resistivity, right? This is the resistivity of the material. But what we hadn't talked about yet is what about if the material changes temperature? So this is going to be here, the resistivity of the material at a given temperature. Because as you increase temperature, increases or decreases, you're actually changing the speed of the atoms. So you're changing how much things are shaking around. And I'll just call that microscopic shaking or movement there is. You're also kind of changing the band structure. You're also changing the somewhat the structure of the so-called conduction bands in terms of what populations of charges might be there. If you give things more energy, then some things might be able to make it up to the conduction band that couldn't make it before. And so for all of these reasons, we're going to then say that so a given material will have a temperature-dependent resistivity, will be impacted by temperature. And so if we go ahead and we can actually just write out this equation for what this is. And so the actual equation for resistivity is going to be equal to some reference resistivity. So this is a reference. So this is, I would call that, I'd assess the resistivity at a so-called reference temperature. Times this factor, which is 1 plus alpha, I'll define alpha in a second, times T minus T naught, where T naught is the reference temperature. So that could be room temperature, it could be freezing temperature, it could be whatever temperature you want. You can put that in this equation is going to be valid. So this is over here on the left-hand side, this resistivity. This is resistivity at the temperature T. So this is our temperature, right? T. And so given a temperature T, we have this equation. And then alpha is the only thing that's unknown here. So alpha is going to be equal to our temperature coefficient. So this is a temperature coefficient of resistivity. So we look what happens in different situations. Let's talk about what happens if alpha is greater than 0. So if alpha is greater than 0, then we can see that as the temperature increases, the resistivity also increases, which means that it's more resistive, and so it's going to be less conductive, more resistive. And so that higher resistivity is going to come from kind of the extra energy loss from the additional motion, at the higher temperature. On the other hand, and so this is actually true for conductors. This is true for things that are already conductors. So things that are already good conductors, they already have a working conduction band. They don't need to be moved into the conduction band. They're already there, and now everything's just moving around more, so it just gets in the way, and then it's harder to get through that space. If we look at the case of alpha less than 0, then we have that as T increases, the resistivity actually decreases. And so this is actually going to become more conductive at higher temperatures, less resistive. And this is actually going to be true for insulators. And this is going to be because what happens with insulators is that they normally don't have anything in their conduction band. So normally, the conduction band, meaning at like lower temperatures, the conduction band is empty. But the higher temperature allows for some charges essentially to enter that conduction band for some population of the conduction band. And so you get some motion of your charges, and it's going to then be going to be a better conductor. Okay, so that's really the key idea, like I said, of this pretty short video, just talking about the temperature dependence of resistivity and how that might look in conductors and insulators.